As we turn our attention to liquids and solids, one of the first things that we should talk about is something we already know. The big difference between liquids and solids and gases are gases take up the volume of their container. What that enables them to do is that they are highly compressible. Liquids and solids do not take up the volume of the container. They have a specific volume, so they're not as easily as compressible as gases are. You can use gases in pistons to drive pistons. You can push down a piston to decrease the volume of a gas significantly. You cannot do that for liquids and solids. So if we start at the other side of this spectrum, is if we think about liquids and solids having a specific volume, we should ask the question, what keeps them together? And what is the difference between liquids and solids and gases? And gases rarely come into contact with each other. They're not, don't have a big attraction for them. And to answer that question, of course, we're going to have to discuss intermolecular forces, or forces between two different molecules. Now, there are four types of intermolecular forces that we're going to discuss. The first of those is actually for a mixture, and that is an ion-dipole force. Now, as the name implies, this is going to be between an ion and the interaction with a molecule that has a dipole, or a polar molecule. Okay, so what are our polar molecules? Remember, those are molecules with a dipole moment, a bond that has a big difference in electronegativity. If those dipole moments do not cancel out, of course, that's a polar compound. Water being a good example of a polar compound. So when you introduce, say, a ionic compound like sodium chloride into water, it actually dissociates, or becomes a sodium cation and a chloride anion. Okay, now, why did it dissociate? Because the interaction between the partial negative charge of the oxygen molecule and the attraction with the positive charge of the sodium cation is what does it. And of course, the partial positive charges associated with the hydrogens are what attracts the chloride ions, and what interacts and pulls them apart and keeps them solubilized. Now, that is exactly the ion dipole forces that we're discussing. It is the electrostatic attraction between the positively charged sodium cation and the negatively charged, partial negative charge of the oxygen within a water molecule, and the electrostatic attraction between the anion and the partial positive charge of the polar molecule. Again, Coulombic forces, or electrostatic attraction, is what ion dipole forces refer to. Now, why would a partial negative charge overcome a full positive and negative charge attraction? Well, it turns out that there's many waters of hydration, as they refer to it, waters of solvation. Excuse me, many waters associate themselves around the anion and cation, and the sum of those partial negative charges, or sum of those partial positive charges, is what keeps this interaction favorable. Now, a second intermolecular force that we're going to discuss is dipole-dipole interactions. And then, as the name implies, it's a molecule with a permanent dipole, so this would be polar, the interaction between two polar molecules. Okay? So let's look at another polar molecule. Let's look at formaldehyde. So formaldehyde was CH2O. We drew this Lewis structure. We know that there's a dipole moment going towards that oxygen atom, a partial negative charge, and then, of course, partial positive charge here. If we sort of cartoonishly draw this formaldehyde molecule as a molecule with a partial negative end and a partial positive end, we know that if we have another formaldehyde molecule nearby, it will have a partial positive charge and a partial negative charge, and it will orientate itself so that the partial negative and partial positive charges interact with each other. And that interaction, that Coulombic attraction, that electrostatic attraction, is the dipole-dipole interaction, or the dipole-dipole force. Okay, it turns out that we're going to talk about the 4 intermolecular forces. Dipole-dipole interactions happens to be the 3rd strongest, if everything else is equal, 3rd strongest intermolecular force. The first strongest intermolecular force was ion-dipole interactions. As you can see, this is the interaction between a full +1 and a partial negative charge, or many negative charges. So the interaction of a full positive or a full negative charge indicates that that Coulombic attraction is going to be stronger than anything that partial charges can overcome. Okay, so because ion-dipole interactions work with full charges, dipole-dipole interactions work with partial charges, of course they're going to be less strong. Now, the second strongest intermolecular forces, why did we go from first to third? The second strongest intermolecular forces happens to be a very specific case of dipole-dipole interactions. Okay, but let's look at one of the many physical properties that intermolecular forces will interact with, and that is boiling point. So we can, as we'll talk about more in depth later, boiling point is determined by intermolecular forces. When you boil something, you're going from the liquid phase to the gas phase. So what happens? What keeping that a liquid? It's of course the intermolecular forces. And if they happen to be a polar molecule, we're talking about dipole-dipole interactions. So dipole-dipole interactions, or you can quantitatively calculate the dipole moment with units of Debs. And as the dipole moment increases, the boiling point increases, meaning that it takes more energy to overcome those intermolecular forces. Acetonitrile, a very polar molecule, it has a much higher boiling point, and is actually a liquid at room temperature, than propane, a molecule that we know is nonpolar, virtually no dipole moment, is a gas at room temperature. Okay, and we'll discuss this further. That very special case of dipole-dipole interactions is referred to as hydrogen bonding. And this is the specific dipole-dipole force which has, when a hydrogen in a molecule is bonded to a very electronegative atom. Most specifically, nitrogen, oxygen, or fluorine. Okay, when this occurs, let's say we've got oxygen bonded to hydrogen. Okay, and let's look at the difference between oxygen bonded to carbon. Okay. Well, we know that there's going to be a dipole moment between the hydrogens and the oxygen, as well as dipole moment from the carbon to the oxygen. The big difference is that hydrogen only has one electron, and it's occupied in that bond, in that overlap of the orbitals between hydrogen and oxygen. And if a hydrogen only has one electron and it's around oxygen most of the time, there's an absence of electrons shielding hydrogen's nucleus. Whereas carbon, even though it's got one of its electrons in oxygen bonds, those electrons are definitely being attracted towards that oxygen atom. Carbon has additional electrons to shield its nucleus. And so what this is, this partial positive strong is very strong. There's very little electrons. There's very little electron density to shield its nuclear charge, so it's almost like saying it's a really, really close to a full positive 1 charge associated with that hydrogen atom. And so when the partial positive charge is really strong, that is going to increase the strength of the dipole-dipole interaction. It's so much stronger than a normal dipole-dipole interaction, we refer to it as something entirely different, hydrogen bonding. Okay, and we'll take a look at a couple of examples to illustrate how big of an effect hydrogen bonding has after we discuss London dispersion forces. So London dispersion forces, actually we should go back and we can say that hydrogen bonding, because it's a special case, it is our second strongest intermolecular force.